Book 61 of 2020 was Why Does E Equal MC Squared by Brian Cox and Jeff Forshaw. So I listened to this book on audio. I have watched one or two documentaries by Brian Cox about physics, and think that he's really good at explaining physics in a kind of accessible way, easy to understand way. Although, disappointingly, it's not Brian Cox that narrates this book, it's Jeff Forshaw. This book's essentially about Einstein's theories of, especially general relativity, because that's obviously his formula, E equals mc squared. And Cox and Forshaw are basically taking you almost like through a tour through science to explain how Einstein came to his theories, because obviously everything in science builds on what's come previously. Without that previous advancement in science, Einstein would have never come up with these theories. So they start talking about theories of relativity and universal time, start talking about like Galileo and Copernicus, who both at a similar time discovered that the Earth wasn't the centre of the universe, and that actually we were going around the sun and the sun wasn't going around us, and not all the planets weren't going around us, they were going around the sun. And they talk about Faraday's electrical currents and magnets. Obviously Faraday's really famous for Faraday cages and for, you know, the lightning rod, discovering kind of electrical current, and how if you put a magnet in a coil of wire it creates an electrical current, which I'm sure you learnt in GCSE science. And they talk a little bit about Maxwell's oscillating electromagnetic fields and the discovery of you know, magnetic fields and kind of wave equations, and how that led to the disproving of this belief in the ether. So that's all kind of like discussed initially to kind of, I guess, lay the foundations of scientific knowledge to then be built upon. And then they start to discuss Einstein's theory of special relativity, and they use the train and platform thought experiment, which is really famous. I'm sure you're probably already aware of it. I'm aware of it because I've read Stephen Hawkins. I never say his name right. I think it's Hawkins. I always say Hawking. I think it's Hawkins. Read his Brief History of Time. I had aimed to buy Brief History of Time, and accidentally bought the briefer one, which is the illustrated version, which was actually quite helpful because then I could see all the kind of diagrams and whatever. So I have in my mind pictures of this kind of platform thought experiment, and actually on the documentary that I watched that Brian Cox did, it was, you know, showing this. So I had a lot of imagery in my mind as I was listening to this book, that I think that if you haven't read anything previously and haven't got these kind of images in your mind already, you might find it a little bit more difficult to follow. For me, this was kind of like all stuff that I already knew, so it was just like, you know, recapping it basically. But essentially this kind of thought experiment is where if you are on the platform and somebody else is on the train, and the train is accelerating away from the platform, will the clocks, so a clock on the platform and a clock on the train, tick at the same rate? So is there an absolute time? Because Newton proposed that there was an absolute time, that it didn't matter where you were or how fast you were moving in relation to somebody else, that time would always be the same for everybody. And this thought experiment, if you use kind of like laser clocks, so that you're not having like issues with like the mechanics of how clocks work, and you know, because all clocks tick differently, don't they? If you use kind of like laser clocks, they're a little bit more accurate, a lot more accurate. I was just thinking then of a documentary that I watched on Netflix by Zac Efron, and they were looking at kind of laser clocks and how they're actually, you know, they're not completely accurate, but they're a lot more accurate than what a normal clock is. But essentially, this kind of thought experiment, and you know, if you do the kind of mathematics behind it, time ticks differently dependent on how each person is moving relative to the other, and so therefore they don't tick at the same rate. and you can basically use Pythagoras' theorem to prove this. Now, it's at this point that on an audiobook it doesn't really work, because Pythagoras' theorem is a really, really easy mathematical theorem. Like, it's not difficult. Like, you know, people in GCSE maths can do Pythagoras' theorem. It's like a squared plus b squared equals c squared, although they use x, y and z, which is really confusing for me because I don't use x, y and z. So it's really, really easy, but when you're listening to it on an audiobook, it was so complex the way that it was explained, and I was just like, that's like, I'm finding it difficult to follow, and I teach this to other people and it's really simple. So I was just like, I think you need to have the book in front of you, and I think you also need a pen and paper to work the mathematics out for yourself to see that this is actually proven, you know, these calculations. I think maths is something that you can't learn in the abstract. Like, you have to actually compute it to kind of see that, yeah, that does kind of fit it. And so my kind of query with this not query, but my bugbear, I guess, with this book is that if the maths is not, if I'm not able to crunch these numbers with actual, you know, data, then why is it necessary to describe it in full in the book? Because if this book is for people who don't really know much about physics, they don't need the maths, because it'll be beyond their comprehension anyway. Because if you know physics, you usually know maths, because they go hand in hand with each other. And then if it's for someone who is good at the mathematics and knows it, then why do they need it? Because this book's really simple for them. So it was a little bit of a like, who's this book aimed at? Like, I'm not really quite sure, because it's like, if you're brand new to physics, the maths is too much. And if you know a little bit about physics, you need to sit down with the maths and go through it and not just be told it. So yeah, it just seemed a little bit weird to kind of put all the maths in as much detail as it was in for one camp, but for the other camp it's not detailed enough. So I don't think that it really worked very well for that reason. But anyway, this whole kind of train platform thought experiment suggests there's a constant speed of light, which is where the c comes from in the E equals mc squared. So that's kind of like building up. And then they start talking about kind of relative time and time dilation and the kind of twin paradox. So another kind of thought experiment is that clocks nearer the centre of the gravitational field are supposed to be slower, so that the twins will age differently to each other if one of them is an astronaut and goes out of space and one of them stays, you know, on Earth. But there's a suggestion from special relativity that due to kind of like the inverse effect of deacceleration, when the astronaut twin comes back to Earth, that they'll have aged the same, and that the passage of time would be the same for both of them. But this later on in the book is revised by the general theory of relativity, which suggests that actually time is moving differently dependent on how you are relative to each other. So for example, the twin that's earthbound, you know, 40 years might have passed for them, but I was like, it's because I'm reading my board and I've just wrote the numbers on. The earthbound twin will have, the 59,000 years would have gone by for them, but the astronaut twin would have only have been gone for 40 years, because as the twin's gone, the Earth's obviously still like rotating. So it wasn't really explained in the book that the general theory of relativity criticises that initial special relativity theory, because when I was listening to it, I was like, oh, they age the same? I'm sure that's not how it works. Like, because I'm thinking of like all the films that show that if you leave Earth and you come back, like Earth's not as you left it, because more time's passed than what you're aware of when you're out in space, because you're away from that gravitational field. And so I was like, that doesn't make sense. Like, this is not what I know about physics. And then when I got later in the book, it was talking about general relativity, and I was like, oh, now it explains that actually my initial thought of it was right. But it was good actually, because it made me realise that what the thought was initially with the special relativity theory, and then what it became with the general relativity theory. So that kind of added to my knowledge. But it would have been nice if you know, Cox and Forshaw had made that point, because I feel like if you didn't know anything about physics and you didn't know anything about that previously, you wouldn't have realised that those two are explained by the different theories. I wouldn't have thought. I only realised because I thought they were wrong. Not that they were wrong, but that they were saying something that was not my understanding of it. So I looked into it and then realised, you know, what was actually happening and why they discussed it like that. It would have been better to have them kind of next to each other. So like talk about general relativity special relativity, do the twin paradox, then do general relativity, so that it bridged it, but they didn't really do it like that. Then they started talking about the kind of preservation of angular momentum of the moon, how the moon is like on an ellipsis with the gravitational pull of the Earth, and that kind of suggests that space-time is invariant because initially Minkowski believed that space-time, so like the Earth, was flat, and kind of used Euclidean geometry to suggest that. But actually, if you use Euclidean geometry on the Earth, because it doesn't, like, you know, the parallel lines don't work and the angles don't add up to 180, it suggests that actually the Earth is curved, so there's a curvature to the Earth, and so therefore you need to use geodesics to kind of calculate space-time. So they was talking about that, and they kind of used like Pythagoras theorem again, and used Occam's razor in the sense that you use like the most simple solution to test it out. So they kind of use like the negative version of Pythagoras theorem to suggest that that's not the correct one to be applied, because that would violate the principle of causality, because he kind of presented it on like there's a circular representation. So this is another problem with the audio, is that a lot of these things are like diagrams that would be really helpful to look at as you learn about them. And in other books that I've read, obviously because I've had the physical copy, I've been able to see these diagrams. When I was writing the review for this, I was looking at all these kind of theories to kind of create the review, and I realised that there was loads of diagrams, and I was like, I should have been looking at these as I was kind of listening to this book, because it would have made more sense. Because the circular representation one I could figure in my head, because as they were describing it, I was like, yeah, if you they were doing kind of like they were using an example. See, this is what's really good about this book actually, is that they use really easy examples to understand the physics principles behind it. So like they were talking about event 1 is when you wake up in your bed at 10 o'clock, and at 11 o'clock you eat your breakfast at the table. So they were like saying event A and event B, and if you put it on a kind of circle with Pythagoras theorem, it ends up being that B ends up happening before A, and so there it violates the principles of causality, because event A must happen before event B. You must wake up first before you eat your breakfast. So it was kind of explaining it like that, so it's a bit easier to understand. And they were kind of bringing in the whole idea of an hyperbola. I don't know if I'm saying that right or not. I was like, I could pronounce this before I was doing this video, but there we go. And I was thinking in my head then of hyperbole. So like, no, it's not, obviously not hyperbole, because that's an English grammar thing. But anyway, so it kind of makes sense when you look on the diagram, but it's quite difficult to grasp it unless your mind works like that. I mean, for me, that circular representation thing worked based on me listening to their explanation, but it would have helped a lot to see the diagram first. From that, they kind of figured that, you know, the speed of light was c, and it was invariant, and they then started to talk about kind of 4-dimensional vectors. Again, I suppose you kind of need to be able to visualise these in your mind and know kind of like what a vector is. I've taught vectors before, so I know what a vector is. So imagine it in a kind of 4-dimension made sense, because then you've got kind of like time as well as the space. So they were talking about space-time velocity vector, and how basically they were using the representation of a light cone and how it moves along the hyperbola. So obviously that you need the diagram for. You need to see the diagram. Like, I was kind of imagining it kind of half right, but when I looked at the diagram, excuse me, it kind of made a lot more sense. Again, there's lots of maths that's explained to kind of support all these things, but you can't just listen to it, and you can't just listen to maths. Like, you have to compute it to understand it. So I think, you know, it kind of reduces I kind of like was listening to them, but I was like, I don't really need to hear these things. Like, I get that you can support it with maths, like, move on, it's done. And then they started talking about kind of momentum conservation and kind of like the dissipation of kinetic energy. So they use the kind of example of billiard balls, like when you roll some billiard boards and they smash into each other, you hear the dissipation of energy into the air molecules as sound, and they kind of like use that to discuss how mass in elements creates chemical energy. So they started talking about kind of like how electrons orbit around an atomic nucleus, you know, as you learn about in GCSE science. And they kind of talked a little bit about Schrodinger's discovery of how you can have kind of like spontaneous conversion of a lighter atom into a photon, and you know how that was kind of discovered. I've actually read a book called Schrodinger's Cat. Is it Schrodinger's Cat? No, it is Schrodinger's Cat is what it's about. I don't think that's what the book was called. Finding Schrodinger's Cat, that's what it's called. So I've read that book that talks about Schrodinger, talks about kind of, you know, lots of other physicsy things that this book doesn't touch on. So it talks about kind of like, you know, light waves and particles and the Slate experiment and all that kind of stuff. But they just basically were using it in this book to talk about the kind of conservation of energy. Spoken a lot about, like, you know, when you burn like wood and it goes into kind of like ash and heat energy, and I was kind of reading it thinking this is really basic science, like you do learn this when you're in GCSE, so it was a little bit like a big emphasis on it. It was odd, this book, because there's parts of it that are really complicated, and obviously the maths is really complicated, and then there's other bits that are just so easy and so obvious and so kind of like, it just made me really think, what, as I was mentioning before, like who is it actually aimed at. Then they also talk about kind of uranium and the loss of mass in terms of creating nuclear energy through nuclear fusion. Was it fission? I've put fusion on my review, but I feel like maybe fission is something as well that's related to that. I'll have to look that up afterwards. I used to know what it was and I can't remember it anymore. And they also talked about kind of carbon dating and using kind of zircon, because obviously it decays, and you can find out then how old kind of like bones and rocks are, I guess. Again, I kind of was aware of all that stuff already. And then they did kind of talk as well a little bit about quantum theory and about how Einstein's theories of special and, well, of general relativity can actually be, in fact, no, I'll come to that in a minute, because I was just the quantum theory that they touch on is kind of like neutrinos and positrons and quarks, but they don't really go into a lot of detail about it, they just kind of mention it. I've also read a book on quantum theory, so I know a little bit about that stuff as well. So they just literally like skated over it, they didn't really go into detail. And they used pulsars as well to you know, use as support for general relativity, in the sense that radio waves kind of like slow as they go kind of like near the different pulsars, to suggest that you've got curved space-time, which is what, you know, the theory of general relativity is suggesting. And this explains why with GPS you've got to kind of reset the clocks, because they run on different time than what is the time on Earth, as the twin paradox showed. And going back to what I was initially starting to talk about, but then realised that I actually were talking about it at the end, is that the quantum theory doesn't support general relativity theory, like they're at odds with each other. So the more that we find out about kind of quantum theory and string theory and things like that, the more that we will probably discredit some of Einstein's theories, perhaps, or maybe they're just, you know, complementary in different kind of ways that we don't know yet, but they're currently at odds with each other. So there's a recognition that, you know, in science everything is being revised as we find out more things. And so I guess it was an interesting book to find out like how Einstein came to the theories and how it kind of, you know, led up to it, and all the kind of history of it, because it takes you through it and it does the maths. But to be honest, I've read a lot of other science books that do it a lot better, and that were a lot, because of the diagrams, and because, like, I mean, at times things are too brief and at times they're in too much detail. And so I think I gave this book 3 stars. I wouldn't really recommend it to read. I think there's a lot of books that do it a lot better. And so, you know, if you want to know about physics and you don't know anything about it, then maybe you'll find it interesting. I did look on Goodreads actually to see what people thought of it, and everyone thinks it's amazing, but I actually think that that's just because people who don't really get stuff like physics, because physics is quite a complicated topic. It's funny actually, because when I was looking at on Wikipedia about this these theories and stuff, just to kind of like write my review, because there's a lot of information, and Wikipedia does it in a really complicated way. Like, if you listen to the book, it's really straightforward and simple, but which is obviously testament to Cox and Forshaw for explaining it really well, because if you look at actual physics stuff, it's really complex, and it doesn't, it's not explained very well, which is why people don't get it very easily. But they explained it really well, that made it really simple to get. But back to my original thing that I was just going to say then, I think sometimes when people get things that are normally quite complex, they either feel really proud of themselves for getting it, so think the book's really good, or they probably didn't get it, but want to tell everybody that they got it, so they think that the book's amazing. And it's like, you didn't really get the book, did you, if you think it was that good? So anyway,